Okay, interesting problem here. Considering this set of functions show that the first statement is correct and the second statement is correct. Okay, so with the first statement, the integral from 0 to 2 pi of the function d theta 1 over radical 2 pi of e to the I m phi is equal to radical 2 pi for all functions that are not 0. Okay, so if the function is 0, we're supposed to get this. If it's not 0, we're not supposed to get this. Why don't we plug in 0, see what we get? This is an extremely trivial thing to do, so I trust most people can figure that out from here. We just plug in 0, this is equivalent to 1. We take the integral of this, it'll just be phi, radical 2 from 0 to 2 pi. This is extremely trivial. I think that this makes perfect sense why this is true. Okay. Now, if we try to solve this with something else. Now, let's go from 0 to 2 pi of e to the I 2 phi times d phi. The integral of this would be e I 2 phi divided by 2I from 0 to 2 pi. Now we know that things are circular in these problems, so e to the I 4 pi over 2I minus e to the 0 to 2I. E to the 4 pi is cosine 4 pi plus I sine 4 pi over 2I minus 1 2I. The sine cancels out, 0. This is just 1. You can see how it's 1 minus 1 all over 2I is equal to 0. Makes sense to me. Now, show that from 0 to 2 pi from d theta of the conjugate and e to the I m theta times e to the negative I m theta would be the conjugate. If these are not the same, it's 0, but if these are the same, it's 1. Okay, the first one is extremely obvious why. The second one is extremely obvious why. If these are equal, you get 1. So if we plug in e to the m, it doesn't even matter what you pick. So cancels out, cancels out. Trying to figure out why it's radical 2 pi, but not, why is it